Hello and welcome to this video. I am Karnesh Johri and this video is about file I/O in Linux. Linux is a Unix-like operating system or Unix-compatible operating system. In the Unix system, there are two basic concepts: processes and files. Unix was the first major operating system to treat ordinary files, directories, devices, network interfaces uniformly as files. So file is a very important concept. Indeed, I/O is important because whatever processing is done, the results need to be communicated to the external world using I/O. In earlier operating systems, I/O was complicated. But in Unix, the complications are hidden underneath and a common simple interface is provided. In this video, we look at I/O concepts and the associated system calls. When we read or write to disk, we do that in units of blocks. The block size is normally 4K, that is 4096 bytes. So if you want to read a byte from a file, the entire block of 4096 bytes is read, and then the relevant byte from the block is given to the program for further work. A similar sequence of steps happen when doing a write operation on a file. The kernel maintains a page cache in the memory, so when you want to read from a file, the kernel checks whether the relevant block is available in the page cache or not. If it is, the relevant block is given from the buffer cache. Otherwise, the block is read from the disk to the page cache, and then the data from the block is given to the program. There is the concept of temporal locality. If a program has accessed a byte in a block, then it is likely to access the next byte soon. So page cache helps in improving the throughput. Apart from the page cache, which is implemented by the kernel, there might be buffering at the user level. If we use the standard library calls instead of system calls, data is read from the kernel in bigger chunks and given to the requesting application program. So the user process need not go to the kernel every time it needs data. The requirement is satisfied more often than not locally by the library. This reduces the context switches of the running process and results in better throughput. Synchronized I/O. When we write to the disk, only the page cache is updated and the block is marked for writing to the disk. The actual writing of the block to the disk might happen later on. Now, in the event of power outage or system crash, there is no time to write the concerned block to the hard disk, and when the system comes up next time, the disk file might not have the latest correct data. This might be a problem in critical applications. So while the page cache speeds up the operation, it might not be sufficient in meeting the requirements of critical applications. For such applications, a program can do synchronized I/O, where when the process executes the write system call, the data is physically written to the hard disk and all the file metadata is also updated. This obviously slows down operations a bit, but might be required for certain applications. Now we look at the system calls for file I/O, and the first is the open system call. The open system call opens a file for further use in a program. The file is identified by the path name, the first parameter. Open returns a file descriptor, an integer which can be used to refer to the file in subsequent system calls. The second parameter, the flags, specifies the access mode, that is, how the file is to be used by the program. It can be ORD only for read only, OWR only for write only, ORDWR for both read and write. There can be more flags which can be odd with access mode. For example, if you specify creat and the file does not exist, it is created. However, to specify creat, you need to use the second form of open system call, which has a third parameter, mode. Mode specifies the permissions for the owner, group, and others for using the file. For each entity, the owner, group, and the others, there are basically three permissions, namely read, write, and execute. And these three permissions can be expressed by an octal number 0 through 7, where 0 means no permission and octal 7 is read, write, and execute permissions. A common permission is octal 755, which specifies read, write, and execute for owner and read and execute for group and others. We can also write rwx, r-x, r-x 755. It was quite common to express permissions with octal digits, but there has been a shift towards using symbolic constants, which is of course more elegant and the right thing to do. So we can express permission octal 755 with symbolic constant s underscore irusr or s underscore iwusr or s underscore ixusr or x underscore irgrp or s underscore ixgrp or s underscore iroth or s underscore ixoth. The last three characters, USR is for user, GRP is for group, and OTH is for others, and RWX are for read, write, and execute. We can make it little more compact by replacing the read, write, and execute permissions by S underscore IRWXU, where U is for user, RWX is for read, write, and execute. So this becomes little shortened and we can rewrite permissions as S underscore IRWXU and followed by ORing of the permissions for group and others as before. Then there is the O trunk flag, and if the file exists and is opened with OWR only or ORDWR, the file is truncated to length 0 bytes. Similar to read, write, and execute for user, we have symbolic constants for read, write, and execute for both group and others, which are SIRWXG for read, write, and execute for group, and similarly SIRWXO for others. Now think about the write system call for a file which has been opened. When write system call returns, the page cache in the kernel has been updated, but the data might not have been updated on the underlying hardware. Now there are two flags, ODSync and OSync, which you can specify by ORing with flags in the second argument of the open system call. If you specify ODSync, it implies that data integrity is to be ensured before the write system call returns. For this, the data has to be written to the hard disk, and also metadata like file size in inode is to be updated so that any program is able to read the data after the write system call has finished. Even if there's a system crash and then system comes up again, any program is able to read the data which was written by the write system call. If you specify OSync flag, it implies that file integrity has to be ensured, which in turn implies that metadata like file modification time needs to be updated on the underlying hardware before the write system call returns. So we see that it takes more time to do synchronized I/O, but it might be required to be done for certain important application. For example, the ledger balance of a bank account must be updated on the hard disk after money has been withdrawn from it. Then there is a create system call which creates a new file with given path name. The second parameter, mode, specifies the permissions for the owner, group and others. If the file exists, it is truncated to size 0 bytes. The file is opened with write only, that is OWR only. So if you look closely, create is nothing but open with flags OWR only or OCreate or OTrunc. Why another system call when open can be used with these flags? Historically, create was a system call to create new files, whereas open with two arguments was for opening existing files. However, with time, it was felt that files need to be created and opened with access modes other than OWR only, maybe ORDWR, and existing files need to be opened for append without truncating to 0 bytes. So open got the third argument and slowly create became redundant, and we can use open for creating new files as well and not worry too much about create. Next, we have the read system call. When a process executes the read call, it reads from file identified with file descriptor fd, the first argument. It tries to read a maximum of count bytes into buffer pointed by buff. On success, read returns number of bytes actually read. It might be less than the count, and that's not an error because only that much data might be available at that time. On error, read returns -1 and error is set to the code for the error encountered. The write system call is for writing data to file identified by file descriptor fd. The data is written from a buffer pointed by buff and count number of bytes are to be written. Write returns the number of bytes actually written, which might be less than what was intended, the third parameter count. This might be due to lack of space on device or the write system call getting interrupted by a signal handler after it has transferred some but not all the bytes. The solution for this is to invoke the write system call again to write the remaining bytes, or invoke write in a loop till all bytes are written. In case of error, -1 is returned and error is set to the error code. The most important point about write is that there is no guarantee that the data has been actually written to the device. It has been written to the kernel buffers, the page cache, and would be written as per kernel algorithms to the device. To make sure the data is actually written, you need to do synchronized I/O as I have said earlier in this video. The lseek system call is used to position a file offset. What is a file offset? A file offset is a position in a regular file where the next read or write operation would occur. A file offset is mostly defined for regular files and not for files like directories, sockets, FIFOs, symbolic links, etc. Some special files, depending on the implementation, might have file offsets defined. So with lseek, we can set a file offset for file descriptor fd. The offset value is the second parameter. The third parameter whence defines a reference for file offset. Whence can have three values. The value seek set means file offset is equal to offset. Whence can be seeker, which means file offset is the sum of current location and the offset value. And whence can be seek and, which implies file offset would be size of the file plus offset. So with lseek, you can set the file offset beyond the end of file. However, this does not change the size of the file. The next read or write operation would occur from this position. When a file is opened without the O append flag, the file offset is 0. Each read or write operation automatically advances the file offset by the bytes read or written. On success, lseek returns the resulting file offset location measured in bytes from the start of file. In case of error, lseek returns -1 and error is set to the error code. Close closes the file descriptor fd. The association between the physical file and the descriptor is terminated. Close returns 0 on success, -1 on error, and in case of error, error is set to the error code. Unlink deletes the path name from the file system. If this was the last link to the file and no process has this file open, the file is deleted. So it is not a problem if a file is unlinked while it was being used by some other process. As long as the file is open, the process can keep on using the file via the file descriptor. Only when no process has the file open, it is deleted. For example, consider this code. This program is for creating a temporary file. We come to the main function. We first find the current time and then we use it for the seed of the random number generator. Then we create the temporary file name, which is /tmp/temp-process ID a random number, and we open the file with creat or oexcl. The file is created, and since oexcl flag is on, this process is the creator of this file. We list the file using the ls command and we unlink it. So the file name is removed from the file system and the ls command confirms that. But we can do IO on this file using the file descriptor. Only when we close the file is deleted. Now we have some buffer flushing system calls. These calls flush the relevant kernel buffer and write to the underlying device. The first is a sync system call. As per POSIX specification, sync schedules the writing of kernel buffers and returns. In Linux, it does more than that. Sync returns once all the pending modification to the file system, metadata, and cached file data are written to the underlying file systems. Sync does not return anything. It is always successful. Then there is syncfs, which is just like sync, but it synchronizes only the buffers of file system containing the file referred by the file descriptor fd. Syncfs returns 0 on success, -1 on error. Syncfs is specific to Linux only. The next two system calls synchronize the memory state of a file to the physical storage on the device. The first call fsync flushes all the modified buffers for the file referred by the file descriptor fd to the storage device. All the data buffers as well as metadata are flushed to the device. After the call finishes, the written data can be read back even if there was a system crash after the call was made. If you do fsync for a file, it doesn't mean that the directory containing the file is also synced to the storage device. To ensure that, fsync needs to be done for the directory also. Fsync returns 0 on success and -1 on error. fdatasync is similar to fsync in that data buffers of file identified by descriptor fd are synchronized to the hardware device. However, some optimization in terms of minimizing data output is done. Only the metadata, which is absolutely essential to read the file later on, is synchronized. For example, file size is written to the inode, but file modification and access times are probably not that important, so that part of metadata need not be synchronized during the operation of fdatasync call. Fdatasync returns 0 on success and -1 on error. Now there are two system calls, truncate and ftruncate, which truncate a regular file to a specified length. Truncate takes a file specified as the first parameter, path, and truncates it to length bytes. Ftruncate does the same to a regular file identified by the file descriptor fd. The process must be able to open and write on the file. If the resulting file length is less than the initial length, extra data is lost. If the resulting length is more than the initial length, null bytes are added to the file. The file offset is not changed. On success, 0 value is returned, and if there is an error, -1 is returned and error is set to the error code. And we come to the end of this video. You can find all this information at https://tiny.1/file-io. Please share this video and subscribe to my channel. Thanks very much for watching. Take care and stay safe.